Welcome to the second session. So Shiraz will give a talk on semi-universality of CFT entropy at large spin.
Thank you very much, Gautam. It's, of course, always wonderful to be back at ICTS. Okay, my talk will be sort of different in style from Loga's. It will be a seminar, let's see how it goes. Okay, my talk is titled Semi-Universality of CFT Entropy at Large Spin and is based on this paper that will appear on the archive tomorrow, along with several correlators, including my excellent student Vipul Kumar, who's looking for a job. Okay. So this is the outline of my talk, and let's just start. As you know, the spectrum of operators of a conformal field theory is perhaps the most basic observable of that conformal field theory. By spectrum, I mean there's a list of all operators with scaling dimension and spin specified. Now, the state operator map of conformal field theories tells us that the spectrum of operators of that theory is the same as the spectrum of the Hamiltonian of that conformal field theory. If I put that conformal field theory on an SD minus 1, take the conformal field theory, put it on ST minus 1, measure the spectrum of energies and angular momenta, that maps to the spectrum of operators as a function of scaling dimension delta and spin. Great. So, if I'm interested in the spectrum of operators of conformal field theory, I can as well read it off from the spectrum of the conformal field theory on an SD minus 1. Through this talk, I will set D equals 4 just for concreteness. Our paper deals with every dimension. Okay. So, let's say that we're in 4 dimensions. The partition function on this SD minus 1 takes the following form. It's trace of e to the power minus beta h minus omega 1 j1 minus omega 2 j2. So what are j1 and j2? You see, we're in a 3-sphere. The rotational group of 3 spheres is SO4. SO4 is a group with two-dimensional group. It's 2 Cartans. j1 and j2 can be thought of as the rotations in the 2 orthogonal 2 planes that you can imagine in the R4, in which you can imagine S3 being embedded. Okay, so this quantity here, in principle, contains all spectral information that you might want of your conformal field theory. Now, through this talk, I will sometimes find it convenient to redefine things a little bit. Okay, instead of working with the rotational velocities omega 1, I will sometimes define what I call a reduced rotational velocity, or reduced angular velocity, nu1, by this formula. Similarly for nu2. And I sometimes define this quantity tau, which is the energy minus j1 minus j2. Okay? So it's energy up after removing a certain amount coming from angular momentum. You will see why this is useful as we go. Okay, beta here is the inverse temperature, and I will call tau the twist. That's more or less standard notation for this quantity. Okay, so the goal of this talk is to try to see what we can say about this quantity, this thermal partition function of a conformal field theory on an S3 as a function of these 3 parameters, beta, nu1, and nu2. Clear? Questions, comments, anytime interrupt me, especially given that this is a mixed audience. Okay, great. Now, while this partition function Z converges over a range of values of beta and the chemical potentials nu I, it doesn't converge for all values of these chemical potentials. So the simplest example of this phenomenon is an obvious one. Recall that in any conformal field theory, the spectrum of energies is unbounded from above at any fixed angular momentum. Therefore, if I take this quantity and make beta negative, this quantity will diverge because this trace will get higher and higher contributions from very high energies will diverge. Okay, so clearly beta has to be a positive quantity. This is the familiar statement that temperatures have to be positive. Okay, however, recent studies of gray galaxies in ADF space have drawn attention to a second such divergence. And this divergence originates from the fact that the spectrum of Ji is also unbounded from above at fixed values of the twist. This may be less familiar to you, but if you think for a minute, the operator del Z, which has energy or scaling dimension equals 1 and J1 equals 1, and so twist equals E minus J1 minus J2 is equal to 0. This quantity has 0 twist, but angular momentum 1. So if I act with that derivative many times, not changing the twist, but I'm increasing the angular momentum. And so the spectrum of J is also unbounded from above at fixed twist. Therefore, if I look at this trace here, it had better be that these news are positive quantities. Okay, if news become negative, the partition function also diverges. Okay, so we've got two criteria for convergence of the partition function. Temperature should be positive and news should be positive. Fine. Now, when you have a quantity and you've got a bound, because if your quantities go beyond a certain thing, some divergence happens. It's usually interesting to study what happens as you approach the edge of this bound from allowed values. Okay, so first let's do it in the familiar case. Let's first do this in the case where we take the edge of the temperature bound. We take beta to 0 from positive values. Beta to 0, remember beta was inverse temperature. So taking beta to 0 from positive values, same as taking the high temperature limit. So what we can ask is, what can we say about the partition function of any conformal field theory in the high temperature limit? Beta goes to 0, but at fixed omega I. Okay, so for the next 5 minutes, we'll focus on this question. 5-10 minutes, we'll focus on this question. Okay. Turns out you can say a remarkable amount. You can say a remarkable amount about the partition function of the conformal field theory just from general principles. These general principles include hydrodynamics. So let me explain. You see, suppose the first thing to say, I've not even written on the slide, it's so trivial, but the first thing to say is that if both omegas were 0, then you want log Z. Because the conformal field theory has no scale, but conformal field theory at high temperatures on a unit sphere, on a sphere should be extensive. The partition function log Z is volume times something. Volume has 3 units of length, is length cube. The only thing in the conformal field theory that can make up this quantity is temperature. So at omega equals 0, your partition function must scale like T cube. This follows from extensivity and dimensional analysis. Okay, some number times dimensionless number times C cube. That's like a trivial thing. How can we improve this at non-zero values of this omega I? Well, if we're at very high temperatures, we have this physical expectation that Loga reviewed for us in his previous talk, that every theory at high enough temperatures is well described by hydrodynamics. So let's use that. Okay, what I want is a solution of hydrodynamics that has settled down, is doing nothing, not producing entropy anymore. Now, in hydrodynamics, the del mu J mu S, the divergence of the entropy current, has a term on the right-hand side proportional to sigma mu nu square, the shear tensor square. Okay? If you've got a solution that's settled down, so it's not producing entropy anymore, sigma mu nu squared must vanish, but because it's a perfect square, sigma mu nu must vanish. And so every equilibrium solution of hydrodynamics must have 0 shear. Now, there's a beautiful theorem one can prove, which goes as follows. The only velocity configuration, take an arbitrary manifold. The only velocity configuration on that manifold that has 0 shear is a velocity configuration in which the velocity is proportional to a conformal killing vector of that manifold. On the sphere, all conformal killing vectors are this guy, del t plus omega 1, del phi 1 plus, I should have put an omega 2 here, plus omega 2 del phi 2 times its SO42 rotations. So we work in a particular conformal frame. So all conformal killing vectors are of this form. Okay, and then you've got to normalize it. The normalization is determined by the condition that velocity squared is -1. Okay, so the only equilibrium solutions have these velocities with an omega 2 here. Okay, what is this configuration? Well, it's a configuration describing a fluid that is rotating in the one direction with angular velocity omega 1 and rotating in the two direction with angular velocity omega 2. As simple as it gets. Okay, this gamma that will appear a lot in my talk is the special relativistic factor, the Lorentz contraction factor, the time dilation factor associated with this motion. Okay, so u mu above solves the perfect fluid equations of motion if you choose the temperature in a particular way. If the temperature is chosen to be a fixed number, any number you want, T naught, times gamma of theta.
Shiraz, there's a cosine square theta d phi 2 square also in the metric?
Yes. Oh, I'm so sorry. There's a cosine square theta d phi 2 square as well in the metric. Sorry for that. Yes. Okay, excellent. So now that we've got the solution, we can evaluate as energy, angular momentum, entropy, anything you want. We evaluate that and go on. S3 times time. Why is omega a killing vector field?
No, why is it a parameter?
Omega is just a number. Omega 1 and omega 2 are numbers. So del T is a killing vector. Del phi is a killing vector. So any linear combination of them is also a killing vector.
But is it with omega 1 and omega 2?
Yes. It's related. It's going to be, you see, it's intuitive, right? When you put that omega beta, it sets it spinning. So you have to check, but it will turn out to be related. Yeah, but excellent question. Thank you. I should have said that. Thank you. This will turn out to be the same as the omega 1, omega 2 in the trace. Okay, so that has now a physical interpretation. It's the angular velocity of the fluid spinning. Okay, excellent. Thank you. Now, so notice that you have exactly as many solutions as you have angular momenta and energies. We have a 3-parameter set of solutions labeled by omega 1, omega 2, and T. And you have two angular momenta and energies. So 1-to-1 correspondence between these solutions and angular momenta and energy. So we find entropy as a function of E, J1 and J2. Okay? Once you've got this, you can Legendre transform it to go to canonical ensemble, and you find log Z. The canonical quantity takes this following form. T cubed divided by 1 minus omega 1 squared into 1 minus omega 2 squared. Okay? This tells you that every conformal field theory at high enough temperatures has this partition function, okay, with one piece of data unknown, namely an overall constant. Okay, one dimensionless number specifies, encodes all the dynamics of the conformal field theory at high temperatures. Everything else is just determined universally. Okay, this was a review. This was worked out maybe 20 years ago by Loga, myself, and various others. And it's recently got more prominence in the conformal field theory community because it was reviewed in this paper by Karen Ho, Simons Duffin and Oguri and others, and sort of given more, brought to the attention of the CFT bootstrap community. Okay, great. I have one last thing to say about this before I get to the main topic of my talk. And that something is sort of interesting, which I only recently realized while writing this paper, though we could have realized it 18 years ago. Recall that in a conformal field theory, you have unitarity bounds. Unitarity bounds are statements of the form, the energy of any state, or the scaling dimension of any operator, is always greater than or equal to something, some number determined by the angular momentum of that state or that operator. Now, the form of the unitarity bound in 4-dimensional conformal field theories is well known, and it is given by the following. E is greater than or equal to the maximum of J1, J2 plus 2 if J1 is not equal to J2. E is greater than or equal to J1 plus 1 if J1 is equal to J2. And E is greater than or equal to 0 if both J1 and J2 are 0. Okay, this is the standard unitarity bound of a conformal field theory. Already, this relationship tells you a little bit more about unitarity. You see, one thing that this thing implies is that it implies, because this partition function is well defined all the way up to omega equals 1, it implies that E minus omega J1 plus J2, I've got this by setting omega 1 equals omega 2 for a simple example, is bounded from below for any omega greater than 1. And if you think this through using the unitarity bound gives you a similar thing because it tells you E has to be larger than some J. But if you put in the factors and work it through, you will find that unitarity only implies the statement for omega up to half. The region from half to 1 is not covered by unitarity. So already this fluid dynamics is telling us more about bounds of energy than the usual unitarity bound. But precisely that this condition is true is implied by the Anek bound of 11. Oh, I put the reference 11 of Cordova and friends. Okay, so what I want to say is that there are sophisticated ways of getting bounds that go beyond unitarity. Hydrodynamics is a much easier way of getting many of these bounds, or at least motivating many of these bounds. Okay, yes.
Probably say what Anek meant.
Anek, average null energy condition. If you don't know what it is, it won't help. Okay, okay, great. Great. Fine. So that's all I wanted to say about the high temperature limit. The rest of the talk, oh, no. Fine. Still sticking to the high temperature limit. I'm now going to rederive this high temperature formula in a slightly more convoluted way, because this slightly more convoluted way will be useful for what I actually want to do. Okay? So, this is, we're going to use the method of equilibrium partition functions, what we called 12, 13 years ago, the method of equilibrium partition functions, and what the conformal field theory community now calls a thermal effective field theory. So I'll try to use that terminology when possible. So the method goes as follows. Consider a conformal field theory on such a Lorentzian spacetime. What's special about this spacetime is that there is no t, no time in any of the arguments of any of these functions, which tells us that del t is a Killing vector. Because we're looking at a conformal field theory on a spacetime with a Killing vector, there's a conserved charge. Because there's a conserved charge, there you can define a partition function, trace e to the power minus beta h. So given any such manifold, you can put a conformal field theory on it and ask, what can you say about this? What can you say about this partition function? Well, we know that this partition function, by the usual rules of quantum field theory, is evaluated by just performing the partition function of the quantum field theory after moving to Euclidean space. So we just perform, we look at this metric, we perform the t goes to minus I tau rotation, and we get this Euclidean metric. And we put our conformal field theory on this Euclidean metric, evaluate its partition function, and that gives us z trace, which is trace of e to the power minus beta h. This is in general true. Now suppose we're interested in this in the high temperature limit. In the high temperature limit, this circle, this tau, which has now become a compact circle of size beta, in the high temperature limit, this tau is very small. Okay? So it makes sense to dimensionally reduce the theory and look at it in 3 dimensions. Okay? Because after you put a generic conformal field theory in 3 dimensions, generic conformal field theory on a thermal circle, this conformal field theory becomes massive. This effective 3-dimensional field theory is a massive field theory. And so if we integrate out its fields, we expect to get a local answer, local in the geometrical data of the manifold. So local in the metric, in the gauge field, and in the sigma field. Is this clear? Okay, so we expect to get that log z is an integral of, well, just a scalar function of sigma plus stuff with 2 derivatives. So the Ricci scalar, Fij, del sigma squared plus blah, blah, blah. Okay, now I filled in the sigma dependencies here. You might have thought I could have any dependence on this quantity sigma, but I filled in the sigma dependencies here using the fact that the conformal field theory is invariance under Wiles rescaling. That completely determines the sigma dependencies of every term in this quantity. Okay, so the e to the power minus 3 sigma cancels the Wiles scaling of G of the 3-dimensional metric, and so on. Okay, great. The point of this expansion is that if our temperature is large, note that this expansion is an expansion in inverse temperatures. Okay, so the point of this expansion is that if a temperature is large enough, the first term is much larger than the second, which is much larger than the third, and so on. This is an expansion in 1 over temperature. Okay. Good. This is some general blah, blah, blah theory. Now let's apply this general blah, blah, blah theory to the manifold of interest, namely S3 times S1. S3 times S1 after a twist. Okay, so this is the metric of S3 times S1. This time I have the d phi 2 squared. Okay, and we are interested in computing this trace e to the power minus beta h plus omega 1 phi 1 j1 plus omega 2 j2. That corresponds to twisting the partition function. That is, computing this partition function with the identifications tau goes to tau plus beta, phi 1 prime goes to phi 1 prime minus I omega 1 beta, and similarly for phi 2 prime. Now in the formalism that I developed before, my metric, my time coordinate, the identification was just in time, not in some mixed coordinate. So in order to make contact with the formalism, I do a coordinate change. I define phi 1 is equal to phi 1 prime plus blah, so on. And in these new coordinates, the identification is just tau goes to tau plus beta, nothing else changes. But the price you pay is that the metric, which was nice and simple here, becomes more complicated in these new coordinates. Okay, now, so we've put this S3 times S1 problem in the language of the thermal effective field theory with particular choices for this e to the power minus sigma, that's gamma of theta, for the gauge field, that's this quantity, and for the base metric, that's this quantity. Okay, using these formulae and doing some algebra, you find the square root of G3, the square root of the base metric, determinant of the base metric, turns out to be gamma times the square root of the round metric on the 3 sphere. So we'll use this a lot. Okay, now, because we're in the high temperature limit, as I explained, in this expansion, we need only keep the leading term. The leading term had square root G3, had e to the power minus 3 sigma. But notice that e to the power minus sigma is gamma, so e to the power minus 3 sigma is gamma cube. Square root G had an extra factor of gamma. So this quantity here, this log Z, is integral over S3 of gamma to the 4. And when you perform the integral, you get 1 minus omega 1 squared times 1 minus omega 2 squared. You can keep track of the coefficients, t cubed times a number. So this more elaborate method reproduced the same answer that we got from fluid dynamics. It's not a coincidence. In fact, this more elaborate method, we developed it 12 years ago in order to constrain hydrodynamics. Okay, so these things are joined at the hip. This is not really a different method. Shiva. It's same, t cube. Okay, that I just didn't keep track of it here, but it's very easy. It comes from the fact that there was a t cube here. Okay, no change.
Shiraz, maybe some. So in the normal Kaluza-Klein that you did, so the Kaluza-Klein mass was T. Now you're doing a twisted Kaluza-Klein.
Yes.
So can I? Is there some kind of spectrum of masses of the non-trivial Kaluza-Klein modes, which when integrated out will naturally give that 1 over 1 minus omega 1 squared times 1 minus omega 2 squared? Is there some understanding? Like
Yeah. So excellent question. So Gautam's question can be translated to, what is the proper length of your identification circle? Right. Okay. So it's interesting. The proper length is very small. Okay. It involves this gamma. Why is that? You see, you're going as t goes to t plus something. But if you look at the identification here, you have phi goes to phi plus I times something. So effectively, this other direction is becoming like a Lorentzian direction. So the length, the identification length is positive plus negative. Okay, so it becomes smaller. And when you compute that, that's gamma. That's 1 over gamma. So that's tightly related to your question. Okay. Excellent. Excellent. So now we are going to forever forget the high temperature limit. The rest of this talk is dedicated to the new stuff, the stuff that's not 20 years old, despite what the conformal field theory community seems to think. And we're going to go to the limit nu I goes to 0. Okay. So still focusing on S3 times S1, we're going to look at log Z in the limit nu I goes to 0 at fixed beta. Okay. Now, the first thing we're going to do first thing to note about this limit is the following. This gamma square factor, which will play a huge role in everything I say, if you compute it, in the limit, both nu's are small. Okay, basically what's happening here is this. Where is gamma square? Gamma square. Here, no. Here. You see, if omega 1 and omega 2 were both 1, this would be 1 minus sine square theta minus cos square theta, which would be 0. Okay? Since omega 1 and omega 2 differ from 1 only a little bit, this tells us that this gamma is going to be everywhere large. Okay? And you can work that out and you find that gamma, I've got this wrong. This should have been the numerator, so sorry. Gamma is 1 by nu, square root nu1, nu2 times a smooth function of theta. So these nu1, nu2 are small quantities. So this should have been on the right-hand side, or this should have been up in the numerator. Sorry about that. So gamma squared is of order 1 by nu times a smooth function. That's what you have to keep in mind. Okay, smooth because we're taking the ratios of these nu1 and nu2 to be fixed as nu1 and nu2 go to 0. Okay. Now, I want to study, I want to see what I can say about log z of this conformal field theory in the limit that the nu1 and nu2 both go to 0. Okay? And irritatingly enough, the way I have of making progress is in using the small beta expansion, even though beta is not small. So this is an irritating thing, and we will come back to it. Okay? But what I'm going to do is to work within the small beta expansion anyway, use this thermal effective action, and see what I can say. So, for the next 2-3 transparencies, we're going to do some algebra. Bear with me. There will soon be a point. You know, what I want to do is to compute curvatures of this 3-dimensional base manifold metric, curvatures of the field strength Fij, and covariant derivatives on this base manifold. And in order to do that, it helps to set up a Vierbein frame. This Vierbein frame is very well adapted to the problem at hand. D theta is in the theta direction. E2 is in the direction of the velocity of the fluid. And E3 is the unique Vierbein vector that is orthogonal to both these other directions. Okay? In these directions, we can just compute all curvatures, all spin connections, and all field strengths, all non-zero, and they're all listed on this transparency. Every non-zero quantity is listed on this transparency. You don't need to know you don't need to look at the details of this. The only thing to notice is this. You look at these Riemann curvatures, Riemann tensors, none of them scale faster than gamma squared. Remember, gamma is the quantity that's becoming big as nu goes to 0. None of them scale faster than gamma square, and while there are quantities like gamma prime, at leading order, those terms that are of order gamma square involve no derivatives. So at leading order, all curvatures are gamma squared and explicitly gamma squared, not derivatives of gamma squared. Similarly for field strength, at leading order, you get gamma squared, no derivatives contribute. Derivatives are subleading. Similarly for spin connections, at leading order, the spin connection goes to gamma, and derivatives are subleading. Okay? So, what I've reviewed for you is this following. By examining the formula in the previous transparency, we find the following. No component of either Rijkl or Fij scales faster than gamma squared. And every term that saturates the scaling has an explicit factor of gamma squared. Similarly, no component of the spin connection, omega ijk, scales faster than gamma. And every term that saturates this has an explicit factor of gamma. Okay? Finally, ordinary derivatives acting on gamma order 1, because gamma was a smooth function. Okay? So ordinary derivatives get their leading contribution, covariant derivatives get their leading contribution from the spin connection acting on things. Okay? So this statement about omega translates into the statement that every covariant derivative, no covariant derivative, scales faster with gamma than gamma, and that this leading order scaling is explicitly a factor of gamma, not some derivative. Okay. With this in mind, now we just put things together. Consider a scalar, meaning a Lorentz invariant quantity Q, that's built out of NR Riemann tensors, NF field strengths, and ND covariant derivatives. Using the scalings that we looked at before, This quantity cannot scale faster with gamma than gamma to the power 2 times nr, because each nr scales like gamma square at most, plus 2 times, oh, there should be nf, sorry, plus 2 times nf, because each field strength scale like gamma square at most, plus nd, where that's the number of covariant derivatives, because each covariant derivative coming from the spin connection scale like gamma at most. Great. Now it looks like we're in danger. Looks like things which are built out of more and more Riemann tensors, more and more derivatives, more and more field strengths grow faster and faster with gamma, so that higher and higher order terms in this thermal effective action will contribute more and more. However, remember that every term in the thermal effective action has to be Weil invariant. So we have to still look at the powers of e to the power minus sigma. So in order to get that, we first have to find what the Weil scaling of this Q term is. Now, look, the total number of lower indices carried by Q is 4 nr, because Riemann tensor carries 4 lower indices, plus 2 nf, because field strength carries 2 lower indices, plus nd, because every covariant derivative carries 1 lower index. Consequently, our quantity must have this number divided by 2 factors of g mu nu, upper metric, in order that all indices are contracted. You could also get similar contraction from epsilon symbols, gives the same scaling. Okay. Now, recall that the Riemann tensor has Weil weight 2, because Riemann tensor scales like is homogeneity 1 in the metric. G inverse carries Weil weight minus 2, and field strength and d mu carries 0 Weil weight. It follows that Q is of Weil weight, okay, minus of 2nr plus 2nf plus nd. Okay, where did that come from? I've added the Weil weight of these derivatives. I mean, the Weil weight of the G inverses and the explicit Weil weight of the Riemann tensor. That made this 4nr 2nr. Okay, and thus this quantity has Weil weight 3 minus this, where I've added the Weil weight of square root G3. Okay, so Weil invariant contribution proportional to Q to the thermal effective action must take the form square root G3 times this quantity, times sigma times Q, to cancel the Weil scaling of Q. Is this clear? This is a key step in the art. But because, now remember that square root G3 was gamma times square root G3 round. So we get we put that explicit factor of gamma in, so this 3 becomes, yeah. Then what I did was I substituted that e to the power minus sigma was gamma. So this quantity becomes 3 gamma to the power 3 minus 2nr minus 2nf minus nd. And then I put the extra factor of gamma from square root G. So it became this quantity. Now notice that this quantity here is exactly the same as this quantity here, but this appears with a minus sign. Since Q scales at most like this, that cancels this. And so we've just concluded that every term in this thermal effective action scales at most like gamma to the 4. And moreover, it's not difficult to find explicit terms at every order in the derivative expansion that do scale like gamma to the 4. Okay, so our keeping track of the temperature in the manner that Shivam was asking about earlier, tells us that our particular term came with some particular power of temperature times gamma to the 4. But the thermal effective action gets contributions from all such terms. And so in general takes the form T cube plus T plus 1 over T blah 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 with some unknown coefficients times gamma to the 4. So the log Z is the integral of this gamma to the 4, and we've already seen that that integral gives us this quantity. And so by summing up this expansion, we conclude that we get log Z is h of t, which is this some unknown temperature depending on these unknown coefficients here, times 1 minus mu omega 1 squared times 1 minus omega 2 squared. So we have reached our final main result as far as the canonical partition function is concerned. The result is that in the large, you remember that the large temperature limit, the partition function of every conformal field theory took an almost universal form, universal up to one number. What can we say about the small nu limit? In the small nu limit, we claim that the partition function of every conformal field theory takes what we call a semi-universal form. Semi-universal because they have universal poles. Every conformal field theory is a single pole in 1 minus omega 1 squared and 1 minus omega 2 squared. But the residue of this pole is not universal. It's theory dependent. Okay. Now, you can ask, what is the content of this quantity? You know, we're expressing something we didn't know in terms of something we didn't know. But the first thing we didn't know was a function of 3 variables. The second thing we didn't know is a function of 1 variable. So while we're not getting full information, we're getting a lot of information. And that's why this is semi-universal behavior. And the semi-universality will become clearer when we move to the microcanonical ensemble. Okay. Now, since we have the partition function, we can take its inverse Laplace transform. But since things are big, we have this 1 over nu1, 1 over nu2, and that's like big. Whenever you have big things and you take an inverse Laplace transform, chances are you just have to do a Legendre transform. That's what happens here. And when you go through that process, you conclude the following. Consider any conformal field theory in the limit J1 goes to 0, J2 goes to 0, J1 goes to infinity, J2 goes to infinity, tau goes to infinity. But J1 by J2 and tau to the power J1, J2 to the 1/3 held fixed. Okay? In that limit, the entropy of the conformal field theory takes the following form. It takes the form J1, J2 to the 1/3 times some function which is not universal of tau divided by J1, J2 to the 1/3. So let's unpackage the statement a little bit. The first thing we want to say is look at this limit again. J1, J2 and tau are all going to infinity. But let's imagine, set in your mind for a moment, J1 equals J2. This tells you that tau is scaling like J to the power 2/3. So though J1 and J2 and tau are all going to infinity, tau is going to infinity slower than J. This is a large J, not large energy limit. Okay? In this limit, the entropy takes this very striking form. Okay? Now, what can you say about this very striking form? Have you seen something like this before? Of course you have. If you look at a theory as a function of energy and volume in an appropriate limit, everything depends on the entropy is volume extensively. Volume times a function of energy divided by volume, a function of energy density. This is what the entropy is telling. This entropy formula takes this form. There is a new emergent extensivity in the theory. That's what it's telling us. With J1, J2 to the 1/3 playing the role of a volume. Well, isn't that a cool result? I find it cool. Okay, fine. Yeah. We did the small beta expansion because that's all we could do. Okay. The end result, because the end result applied at every order in the small beta expansion. We presume it applies as an exact result. Now, one of my collaborators, Tridib is mathematically inclined, and he'll point out 20 problems with this statement. Limits and integrals may not commute and so on. They may not commute, I forget about them, So, if something applies to all orders in an expansion, sounds reasonable that it will apply in the free theory. Okay, but we will see potential trouble in this. Okay. By the way, since our result makes no mention of small beta expansion, it suggests there is a better argument than the one I've given you that doesn't first expand in beta. It's just that I don't know how to find it yet. Okay, great. Let's move on. So our main result, the main result of this talk is this formula and this formula. Notice that this also expresses semi-universality because once again it takes a function of 3 variables and expresses it in a function of one variable. There's a clear if you know h of t, you can go to S int and vice versa. They're roughly Legendre transforms of each other. You'll find the details in my paper. Okay. Now, Shivam's question raises the fact that this is not quite a derivation. Okay? And we will see another possible problem. So it's good to check it. So in the rest of this talk, I'm going to confront this prediction against 2 examples where we do actual checks. The 2 examples are sort of like antipodally opposite. The first example I'll study is the theory of a single free scalar field. It's the most trivial quantum field theory you can study. We will find surprisingly interesting behavior in this trivial example. The second example I'll study is n equals 4 Yang-Mills theory at infinite, very strong coupling. So free, very strongly coupled. where I will study it using gravity. Both examples, we will see that our predictions are met. Both examples will see some interesting structure and stuff. Let's move on. Okay. So, now the reason that this free theory is particularly interesting is this. We recall that our derivation proceeded via this thermal effective action. Now, the key assumption of this thermal effective action was that when you put a conformal field theory on a thermal circle, the lower dimensional theory is massive. And that is generically true. But it's only generically true. And a counterexample to that is a free boson. So you put a free boson on a circle, you still have a zero mode, which is massless even in 3 dimensions. So the free theory is a theory for which this thermal effective field theory logic doesn't quite apply. So it's interesting to check whether the result still works, even though our derivation didn't work. Okay? And why do we study n equals 4 Yang-Mills theory? Of course, we study n equals 4 Yang-Mills theory because it's the best theory in the world. So you should always study it. Okay. Okay, great. So for the partition function of a free Taylor field theory on S3 is totally trivial to compute. Loga could give it as an assignment in his next quantum field theory exam. It's totally trivial. Okay, and I won't bore you with the computation. You do the computation, 2 things come out. A, our general prediction is borne out. B, we get a formula for this function h of beta. This is the formula. Okay, this symbol d/n means d divides n. Okay. Pretty simple formula. Okay. However, there is already a great deal of rich physics in this formula. The first thing about it is that though this term, I didn't even tell you about it, but in this thermal effective field theory, this equilibrium partition function, you only get even after the you only get suppression by even powers of temperature, never by odd powers of temperature. Okay. Here, this is what you would expect from thermal effective field theory. This is what you'd expect from thermal effective field theory, and this you'd expect from thermal effective field theory, but not this. And that comes from the massless mode, the mode that was not thermal effective. Second, when we look at this has this rich structure of non-perturbative corrections. Okay. Now, this is sort of plenty weird. You've got a terminating perturbative expansion and yet lots of instanton corrections. Okay. Okay. So, sort of weird. Now, these 3 terms were governed by our previous argument, and of course, it worked because of that. This term was non-local. These terms were also non-local, I'll tell you more about that, were not governed by our argument. But they continue to work, meaning they don't spoil the scaling, which I find nice. Now, I will just give you 1 minute more about these terms, just because it's sort of fun, not because it's very important. In our paper, we tracked out these terms. Let me explain to you how they work. You see, these terms are non-perturbative in the small beta limit. So let's work as beta goes small. When beta goes small, our thermal circle is very small. Imagine we do a Kaluza-Klein reduction on this thermal circle. Then you get a lot of very massive modes in 3 dimensions. Now, we want to compute a determinant because a free theory is just computing determinants. But computing a determinant of a very massive field it's convenient to work in well-line formalism. Because in well-line formalism, the mass sits outside the action. And so if the field is very massive, then classical well-lined saddle points dominate. Okay? So in the zero mass, in the zero temperature limit, we can analyze these determinants for these heavy fields in the well-line formalism. Now, there's a trivial instanton to this, a trivial sort of saddle point to this, which is the well-line mapping to just 1 point. But there's also there are also non-trivial saddle points, which are well lines that wrap the equator. Okay? And those are the origin of these points. In more detail, we find a non-trivial well line instanton, which is a particle winding around the equator. And the action for this instanton has 2 contributions. There's a length contribution, which is proportional to mass, and a charge contribution, which is proportional to the charge of this mode, Kaluza-Klein charge of this mode, and the gauge field. The length turns out to be of this form. The charge part also turns out to be approximately of this form. Now, each of these are very large as gamma goes to infinity. So each individually would have suggested that this would give you something that is non-perturbative in the large gamma limit, so not of interest to us. But these 2 things delicately cancel each other to make the total action 2 pi squared n by beta. Okay, and that explains these terms. The fact that this contributes to this h of beta tells you that the contribution of these instanton also has a factor of 1 over nu1, nu2. Because remember that h of beta, remember that h of beta has h of t divided by nu1, nu2. Okay, and these nu1, nu2 term come from 0 modes or almost 0 modes, 0 modes or almost 0 modes around this instantonic action. Now, I've said this in so much detail for the following reason. I told you that this was a theory where this thermal effective action didn't quite work. And we saw that in the answer. We saw these weird results in the answer, these and these. These clearly go away because they come from the zero mass mode. In an interacting theory, this will go away. What about these? They also, we believe, go away. Because you see, you remember that these contributed at leading order in the gamma goes to infinity limit because of a delicate cancellation between mass and charge. Now, interactions don't renormalize charge, but they renormalize mass. So if they renormalize the mass upwards, as we expect in physical grounds, that cancellation will be obstructed. So these will also go away. So both these weird features, we believe, are features of the free theory. Will not persist in interacting theories. You will see an example in a minute. But it's sort of nice that even when our argument didn't work, the final result did, which suggests that the final result is more robust than our argument. Okay, right. Okay. You guys are thinking we've come to a talk on hydrodynamics and somebody's telling us about free field theories. This is very boring. Let's move on to interacting field theories. Okay. Let's move on to n equals 4 Yang-Mills theory. Okay. Now, we want to study the same regime in n equals 4 Yang-Mills theory. We are interested in a very high angular momentum and also high energy limit. Maybe tau is less high than angular momentum, it's very high. Now, if the generic expectation that sort of was implicit in Logas talk is that n equals 4 Yang-Mills theory from the point of view of the bulk in high in the limit where things, you've got a lot of energy, a lot of angular momentum, is dominated by a Kerr-radius black hole in 5 dimensions. Just as a side remark, you also have black holes that clump on the S5, but those are expected to be relevant only at low values of charges, not in this high charge regime. Okay, now these Kerr-radius black holes are parametrized by 3 parameters. Okay, roughly angular momentum and mass, but when you look up the papers that look at their solutions, as anyone here who studied these solutions knows, they're parameterized by these 3 quantities, A, B, roughly angular velocities, we'll come to that, and M, which is roughly the mass, very roughly. Okay, the outer event horizon of these black holes obeys this relationship. So there's a cubic equation for the outer horizon, event horizon square in terms of the mass, and A and B. Now, since it's harder to solve for R plus in terms of mass than M in terms of R plus, what we will do is to think of these family of solutions instead of being parameterized by AB and M to be parameterized by AB and R plus. These are equivalent things, just algebraically more convenient. With this convention, okay, it's easy to convince oneself that the black hole limit that takes us to the semi-universal limit is the limit A goes to 1 and B goes to 1 at fixed values of R plus. Okay, in this limit, I work out to leading order the thermodynamic formulae of these black holes. They're given here. The key point here is that when you take these first you see that when delta A and delta B are small, J is becoming large. Second, you see that tau is also becoming large, but less large because 2 factors rather than 3. So the key point is that tau divided by J, JB to the 1/3 in this limit gets rid of this delta A and delta B. It's only a function of R plus. Similarly, for S divided by J, JB to the 1/3, it's only a function of R plus. So you can take this relationship, use it to solve for R plus in terms of tau. We have an explicit solution in our paper. Plug it back here, and that gives you an explicit formula for S as a function of this tau divided by J, JB to the 1/3. Now, tau divided by J, JB to the 1/3, just one second, is a mouthful. The rest of this talk, I'll call it the scale twist. Tau divided by J, JB to the 1/3 is scale twist. Good. Where did the n come from? N, as far as we're concerned, it comes because, you know, gravity has n. But as far as we're concerned, n is a constant. So it doesn't affect scalings. Okay, it comes because of Newton's constant. So you could have put the n here if you wanted, but it's there. Okay. Excellent, excellent. That was a microcanonical ensemble. We can get similar formulae in the canonical ensemble. We can get the formula for the rotational velocities, the temperatures, and log z. Okay, all good. Once we do that, we can do the same thing that we did before. That is, we can eliminate R plus in favor of the temperature, plug that back into this log z, and we finally find that the partition function takes our predicted form with this value of the function h of beta. Note that this value of the function of h of beta is much more civilized than the free value. It's got a power series expansion in even powers of beta. It has no non-perturbative terms. It's exactly what you'd expect from an interacting theory. Okay, excellent. Now the last thing, last 2-3 minutes. The key point here is the following. Something I want you to note in these formulae is that R equals 1 is a very special place. The first reason that R is equal to 1 is special is that log z, which is proportional to h of R, flips sign at R equals 1. Now, log z being positive tells you black hole dominates over gas. Log z being negative tells you gas dominates over black hole. So this tells you that R equals 1, which is, when you work it out, T is equal to 1 over 2 pi, is the Hawking-Page transition temperature in this limit. The second thing that's special is that R equals 1 is the place where omegas switch sign. Now, the last time I was at ICTS, I gave, or maybe the second last time I was at ICTS, I gave this talk on gray galaxies. One of the key points in my talk was that any black hole in ADS space with omega greater than 1, so with omega the wrong sign here, delta omega the wrong sign. Delta omega, by the way, omega A is 1 minus delta omega A. So if delta omega is negative, omega is greater than 1. Any black hole in ADS is unstable if its angular velocity is larger than 1. So the second thing that we see is that these delta omegas, that the black hole also becomes unstable as T goes below 1 by 2 pi. Now this is different from what normally happens. What normally happens in the Hawking-Page transition, let's say 0 omega, is that in the canonical ensemble, you have the black hole becoming subdominant to the gas. But in the microcanonical ensemble, as you go below the Hawking-Page temperature, the black hole still dominates. It's completely fine, no instability. In this limit, the Hawking-Page transition temperature is also an instability transition. So below that temperature, the black hole cannot dominate. Okay, something else must dominate. And those of you who were in my talk from 2 years ago on gray galaxies know the answer to what dominates below this temperature. They're gray galaxies. Okay, so you can work out the thermodynamic. Okay, now in this limit, something very interesting happens. The whole gray galaxy phase is fixed at one single temperature, 1 by 2 pi. And the entropy of the gray galaxy turns out to be just linear in tau, independent of J1, J2, which also obeys our scaling form because of the interesting identity that if you okay. And so we get a second phase, this gray galaxy phase. Then if you further lower the twist, at some point you reach a place where the black hole in the gray galaxy shrinks to 0 size. And then you descend into a gas phase. And I haven't given you a formula here, but the gas phase also obeys our prediction. So in this limit, n equals 4 Yang-Mills theory has a very interesting phase diagram, which is very highly reminiscent of what happens when water boils. So let me remind you. The phase diagram described in the subsection has a close similarity with that of boiling water. The fixed number of water molecules n is analogous to the fixed n equals 4 Yang-Mills angular momentum. The internal energy of the water is analogous to the twist of the n equals 4 system. And the extensivity of the water, the fact that the entropy of the water is n times a function of internal energy by n, mirrors the new extensivity of the n equals 4 Yang-Mills theory, entropy, namely that entropy is J1, J2 to the 1/3 times a function of tau divided by J1, J2 to the 1/3. Okay. Now, the black hole phase is analogous to the steam phase. Just as we reach the condensation point of steam at 100 degrees Celsius upon lowering the internal energy, in the same way, we hit the super-radiant instability of the black hole at temperature 1 by 2 pi. Okay, now with water steam, if you continue to lower the internal energy, you get for a while you get a phase that is half gas, half steam, half steam, half water. Here you get the gray galaxy phase, which is half black hole, half gas. Very similar. Okay. While you're in this half water, half steam phase, temperature stays 100 degrees. Here in this limit, it's not true for all gray galaxies, but in this limit, the gray galaxy temperature stays fixed at 1 by 2 pi. And then once you've got enough energy so that all the steam disappears, so once you've got enough energy so the black hole has gone away, you now just get a gas phase. I'll be in 2 minutes. I'll be 2 minutes and done. Okay. So it's a very similar phase diagram to water steam, and not surprising. The thing that is new is this new emergent extensivity. This extensivity is governing this new physics. So even if you don't care about conformal field theory, universality, I feel this is an interesting new limit of n equals 4 Yang-Mills theory, which will have interesting new black hole type behavior, may have an interesting generalization of fluid gravity. And I think it's very interesting to study. Of course, this is just my unbiased personal opinion. Okay. Now, there are some caveats here. We've worked out this phase diagram ignoring interactions, and there's various things to say, but I don't have the time to say it. And last statement is that I presented this paper, I presented this talk entirely in d equals 4, and entirely with a very symmetric scaling limit. Nu1 and Nu2 both go to 0 with fixed ratios. You can generalize this to go to different dimensions. You can generalize it to less symmetric scaling limits. Every time you get sort of similar answers. You can look at my paper for details. One comment I wanted to make is that every time except in d equals 2. D equals 2 stands out as special for several reasons. First, everything was already known in d equals 2 because modular invariance allows you to compute things without thinking. Okay. The second thing about d equals 2, but you can ask what is special about d equals 2 from our point of view, from the point of view of this thermal effective field. And if you think about it, it is a very simple thing that's special. You see, d equals 2, the base manifold is 1 dimension. Now, in 1 dimension, there's no Riemann tensor. There's no interesting curvature. In 1 dimension, there's no field strength. There is a scalar field chi, but while invariance completely determines the behavior of that, the partition function in terms of that scalar field. So this thermal effective action in 2 dimensions is just completely determined. There's no ambiguity, no freedom. And so this h of t function is just completely determined in 2 dimensions. It's actually determined to be a constant. It's very boring. The lesson from that is that it's a familiar lesson. D equals 2 is often not a good guide to physics in d greater than 2. That's the main lesson about d equals 2. Okay, conclusions. There are many, many open questions. Can one find new non-trivial checks of a conjecture? Maybe using vector type large N theories in d equals 3. Should be possible, it would be interesting. Can we find a proof of our central result without resorting to a power series expansion in beta? I find it very ugly. We want to find a result that is true at all temperature, and we have to do a power series expansion in beta. We use that to be able to use locality. It feels like we should be able to do better. I don't know how, but yeah. Can we find an interesting scaling limit that interpolates between the scaling limit of this paper and the scaling limit of the light cone bootstrap? Not sure anyone here knows what that is, so we'll skip that. Loga does, but okay. Do black hole solutions simplify in the limit under study? Any hope that one can generalize these solutions in a dynamical manner a la fluid gravity? You see, we're going to I wanted to emphasize that we're getting a universality at temperatures order 1. This is not where we normally expect fluid dynamics to work. So all of this talk, all of the new part of this talk is beyond normal hydrodynamics. That's why we got this h of t function. Got contributions from all orders in the derivative expansion. Fluid dynamics is when one order dominates. Okay, so this is new. This is interesting. It's just equilibrium physics so far, so that's a bit boring. Maybe if we can do some dynamics in this regime, it might be totally new. Okay. Can one find interesting interacting gas and gray galaxy solutions that reproduce the non-interacting solutions at j greater than n to the 6? I haven't told you about these interactions, so we'll skip this part. And is there a similar story? I've studied large angular momentum. There might be a similar story with large charge. There might be a similar story with supersymmetry for indices. We leave this all to future work. Okay.
Yeah. You kind of in the end point out the analogy with the water boiling and the phase diagram of that. But do you have anything? I mean, for example, there are systems like dry ice and dry ice which have this weird phase diagrams, this supercritical phase and all, right? I mean, what sort of, if somebody wants to think of that way through a black hole picture?
Okay, I will take a pass on this one. I mean, already the analogy with water boiling is adventurous. I'm not going there. Yeah. Okay.
So Shiraz, so you found this soap bubble solutions in large D. So that's another different thing which was different from fluid gravity.
Yeah.
So is this like another such?
Yeah, excellent question. In our discussion section, we have this comment that perhaps the place where it will be easiest to find dynamics, this stuff applies at all T.
Yeah.
But if you want to make this dynamical, it feels like the simplest place to start is large D. Because there, as you said, the dynamics goes beyond hydrodynamics. So maybe that's the first place to start. I'm hoping that that will be a crutch and that we can find something new, dynamical at all D. But maybe it's too much to hope. I'm not sure. Different days I did think differently.
Okay, if there are no further questions, let's thank Shiraz for a great talk.